We still have to write a simple recursive function that computes the sum from 1 to n, and we noted that there are certain things that a recursive function has to do to be able to implement useful recursion. So a recursive function calls itself with a smaller problem to solve, and eventually the problem should be small enough that the program, or the recursive function itself should exit and unwind the recursion. We saw an example of that in the last video. So I can't repeat this too many times. Every recursive function has to first call itself. That's what makes it recursive. And if you want that recursive function to stop calling itself, basically you need to call it each time with a smaller problem, and eventually a small enough problem that it can stop the recursion. So the key is to break a big problem into smaller pieces that look exactly like the original problem. That is the key. So for our add function to compute the sum from 1 to n, you can solve that by finding the sum from 1 to n minus 1 and then adding n to it. So the sum from 1 to n is exactly equal to the sum from 1 to n minus 1 plus n. And that's actually what we did with our recursive function. We said this is the sum from 1 to n minus 1. We add n to it and we get the sum from 1 to n. And how do we solve this? Exactly the same way. Turns out internally what happens is you get n minus 1 put into here, and now you're solving the sum from 1 to n minus 1. That's done by adding, in this case, now n will be n minus 1 plus sum from 1 to n minus 2, and so on. So here's the thing. You've broken that big problem of finding the sum from 1 to n into smaller pieces. In this case, just one small piece that looks like the original problem plus the addition of this one last thing. And how do you solve the sum from 1 to n minus 1? The same way. The sum from 1 to n minus 1 can be solved by finding the sum from 1 to n minus 2 and adding n minus 1. Okay, now I would like to have you try to set up a function, a recursive function. If you want, you can do the iterative version first and then do the recursive version like we did in our last video. But you could just go directly to the recursive version. So I want you to write a function that will compute the factorial. So remember, the factorial of n is defined as n times n minus 1 times n minus 2 and so on up to 1. By definition, this is the mathematical definition of factorial. So it looks a little odd, but this is the math. This is how the math works. 0 factorial is defined as 1. Okay, and we can use that in our base case. So to compute the factorial, we can compute it recursively by saying n factorial is n times n minus 1, so on. And that is equivalent to n times, here's the punchline, is the rest of this stuff, n minus 1, n minus 2, so on, is n minus 1 factorial. So now this big problem of finding the n factorial looks like it can be done with a simple operation and a smaller problem that looks just like the big problem. That is, if you can find n factorial, you can certainly find n minus 1 factorial. So why don't you find the n minus 1 factorial first and then multiply it with n and you get n factorial. So you do this smaller, and this is where the recursion occurs. You do this if n is greater than 0. If n is equal to 0, you say n factorial is just 1. How do we get that? That's from this mathematical definition, which says 0 factorial is just 1. We could also say 1 factorial is 1, and either one would work. You just don't want to get to a point where you need to compute 0 factorial and then let's say you don't know what it is. And as a matter of fact, it's 0 factorial is just 1. So In the next slide, I actually have a solution for this. So if you want to try this without looking at the solution, definitely I would encourage you to try to write this factorial function without looking at the next slide. But if you are not sure, you can just move on to the next slide and it'll show you a C++ function that computes the factorial of an integer, n. Okay, so here's how you do it. You set up, instead of add, you just use the factorial function, same parameter, same kind of base case. I took out the cout. And then here I've broken it down into steps. I say here is the recursive call to factorial. I use that in this expression, multiply that factorial n-1 with n, and that should give me the result, and I store this in a variable named result, temporary variable inside this function, then I return result. What do I do? This actually turns out, once again, I could have fewer steps. I could definitely put this factorial here, this call to factorial, I could put it here directly, and then actually I could put this entire expression into here directly. And then you can notice that it's just an if statement with a return and then a return, and I could collapse this all down into one statement using the ternary operator. So even though this can be a lot less verbose, or it can be a lot more succinct, it's nice to have all of these broken down into steps the very first time you do recursion. So just keep in mind this is all probably a little bit more wordy than it should be. It could be a lot more succinct. Okay, so in the next few slides I'm going to show you this box method, and this is a method that's used in many data structures books. It's not used in the Savage book, but not exactly the same thing, but something very similar is in the Savage book. So just hold on for a little bit, because I'm going to show you how to set up this function and run it. And I'll show you how you can transform this add function to the factorial function. So all you have to do is, well, first of all, you might want to change this name. I'm going to see if I can do this. I'll rename this add function to factorial. Okay. So with one thing, I changed all of that, and then I leave the cout in. If n is equal to 0 now, instead of returning 0, I return 1, because that is the mathematical definition of 0 factorial. 0 factorial is 1. And also, if what you will see is, well, I'll set this result. Oops, result is equal to 0, and then I'll say result is equal to n times n factorial. That's actually the only difference, the only real difference between add and factorial, is that sum used addition, factorial uses multiplication, and also the base case should be a 1. If we left the base case at 0, what we would do is multiply. We'll do a lot of work to do this recursion, and we will compute the factorial of n-1 and so on. Eventually we'll get 0 factorial. If that were 0, then this whole thing would just be 0, because you're multiplying. And so it's a good thing 0 factorial is 1, and now we get the right answer, I hope. Let's try it with a small number that we can manage, like 3. Let's compile it and run this. 3 factorial should be 3 times 2 times 1, which is 6. And we can see that it was actually called with n equals 3 originally, and then that was the original call from here. It called itself with 2, called itself with 1, called itself with 0, and then it unwound the recursion, came up with the answer 6. And we know that now if we use n equals 4, this would just give us 4 times 6, which should be 24. Okay, and so on. You should be able to figure this out. So definitely do this on your own, just so that you can see how to write you get more practice writing recursive functions. You can also try using iteration. Iteration is a lot more simple, but pretty soon you will see that factorial is not, recursion is not that bad. Once you get the hang of it, it really isn't that bad. So here's the box method. Oops, let me go back. So when the program runs, you want to represent each call to a function by a new box. So you draw a box for each time you call the function. And that's analogous to our debugger. So remember when we debug, and let's just do that right now. Go to the debug perspective. Here we are. It's waiting for us at the first line. And we can do a step over, and then let's see what happens when we what happens to the stack when we step into the first call. We get this box, and inside that box we have a value for n, which is 4, and result is some random value because we haven't initialized it. Okay, so now our random value goes away. Here's our result initialized to 0. Now we're going to call factorial from inside factorial. So we'll step into, and we get another box in which the value n is 3, result is 0. Okay, so you want to keep this in mind. You have a box every time you call this function, whether recursively or not. So the first time we didn't call it recursively, we were just calling it from main. After that, the function calls itself recursively.